Section 21.4. The shape of the transition state in square planar complexes. If you compare the structure of a square planar complex and the structure of a tetrahedral complex, it may confuse you because in the square planar complex, the bond angles between the ligands are 90 degrees. In a tetrahedral structure, it's 109.47 degrees. Based on VSEPR theory, the tetrahedral structure is favored. But in the square planar structure, I want to remind you, the dz squared orbital feels less repulsion, almost zero repulsion from the four ligands. So there is energy decrease due to the formation of the square planar complex. So if you recall, in an octahedral complex structure, you have 6 ligands. And then if you remove 2 ligands, one from the top, one from the bottom, that will dramatically reduce the repulsion the dz squared orbital feels. This is crystal field theory. And then that will drop the energy level of dz squared to below the barycenter, and even far below the barycenter. If we have a 4D8 or 5D8 transition metal complex, and then this 8D electrons will occupy dz squared orbital, and of course dxy, dyz, and dxz as well. And I want to remind you, dxz and dyz orbitals will also undergo energy decrease because they are somewhat pointing to the g direction as well. The removal of the 2 ligands in the z direction will also reduce the repulsion felt by dxz and dyz. And then this 8d electrons will occupy this 4 different orbitals, dz squared, dxz, dyz, and dxy. What about dx squared minus y squared? In crystal field theory, this orbital feels strong repulsion from the 4 ligands. Thus, this dxy squared minus y squared orbital points directly to the 4 ligands in the xy plane. In ligand field theory, this dx squared minus y squared orbital is the anti-bonding orbital with higher energy than the barycenter, than non-bonding orbitals. So that's why this dx squared minus y squared orbital will be unoccupied. And that's why if you see a square planar transition metal complex, 99% of the chance the transition metal is 4D8 or 5D8. For example, rhodium 1+, iridium 1+, palladium 2+, platinum 2+, or gold 3+. So now let's look at the transition state of the ligand substitution reaction of a square planar complex. Subsection A, the trans effect. A strong sigma donor or pi acceptor stabilizes the transition state in a square planar complex and accelerates the substitution of a ligand that lies in the trans position. So really, if you see a square planar complex, look for a strong sigma donor such as hydrido substituted phosphenol. It's better to have this R to be those alkyl groups because they are electron pushing groups. They help this phosphenol ligand to give away electrons. And this is thiocyanidal ligand with a negative charge on nitrogen. Those are very strong sigma donors. And then you look for the ligand that lies in the trans position of these ligands. These 3 are very strong pi acceptors. This is ethylene or ethane, carbonyl ligand, and cyanidal ligand. All 3 have empty pi star orbitals that can accept the electrons. And this is called pi back bonding because in this case, the transition metal donates electrons, d electrons, to the empty pi star orbitals of these molecules. All right, and also in this case, if you see those strong pi acceptors, look at the ligand in the trans position, and that ligand will be replaced. Subsection B, steric effects. This is quite obvious. If you have 4 bulky ligands in the square planar complex, dissociation mechanism is more likely than the association mechanism. One example of a bulky ligand is tricyclohexyl phosphonoligand with 6 cyclohexyl rings on each phosphorus atom. And then you have 4 such ligands, and then you have 12 rings. Another example is triphenyl phosphonoligands are really bulky ligands. In those cases, the dissociation mechanism is more likely to occur than the association, because it's very difficult for the entering ligand to form a bond with the transition metal before the leaving group actually leaves. So again, this steric crowding effect is quite obvious. If you have bulky ligands, the dissociation mechanism is much more likely than the association mechanism. Subsection C, stereochemistry. So if you look at a ligand substitution reaction of a square planar complex, and if you see 2 ligands before the reaction, in the transposition after the ligand substitution reaction still remain in the transposition, and then very likely it's an association mechanism with this transition metal center forming 5 bonds. Okay, 5 bonds in the intermediate structure. So why 5 bonds? Well, this is because this entering ligand forms a bond with the transition metal center. Meanwhile, the bond between the transition metal center and this leaving group is not broken. All right, so this is the intermediate of the association mechanism. Could this be interchange mechanism? Yes, but then in that case, this is just partially formed, and this bond is partially broken. So in an association mechanism, it is more likely for these 2 gray spheres to remain in the transpositions. Now, what about dissociation mechanism? Well, in the dissociation mechanism, this green sphere leaves this transition metal first, and then this transition metal is bonded to only 3 ligands. 1, 2, 3. The bond angles between those ligands would be 120, 120, 120. And in that case, the entering ligand can attack this transition metal, between this 2, or between this 2, or even between this 2 gray sphere as well. If this orange attack the transition metal between this 2 gray sphere, all right, this 2 gray sphere will remain in the transposition. But it's also very likely for this orange sphere to attack this transition metal between this pink and the gray, or between this pink and the other gray. In that case, the 2 gray spheres will be pushed closer to each other and form a cis configuration. Okay? So if it's a dissociation mechanism, it's more likely actually for the 2 gray sphere to occupy the cis position instead of the trans position. So if you get 99%, trans in the product, well, very likely this mechanism is an association mechanism, and the intermediate has a trigonal bipyramidal structure. Now there's an exception. What if this step has a large energy barrier? So from here to here, it takes a fairly long time to go from the intermediate to the square planar. Well, it may happen, even if this one has lower energy than this one, but the energy barrier can be large, right? The energy barrier can be large. So if the forward activation energy is large for the second step, well, we'll have a long-lived intermediate. Whenever you have a long-lived trigonal bipyramidal structure, please remember the axial positions, okay, and the three equatorial positions may exchange. Okay, why is that? Well, it's pretty simple. This trigonal bipyramidal structure can become a square pyramidal structure easily. Why? Look at the three ligands in the equatorial positions. The bond angles are 120, 120, 120, right? So you can just bend two ligands, any two, okay? And then you can form maybe 90 degrees here, 90 degrees here, and then these two ligands will be 180 degrees, okay? Or you can make, this 90, okay? And then this two will be 180, all right? In that case, you get a square pyramidal structure, okay? So let's say let's make this two 180, okay? 180. This 90, this one 90. And then this green sphere becomes the axial ligand. The other four will become the basal ligands in the basal positions. So again, in a square pyramidal structure, the ligand on top is called the axial ligand in the axial position. The other four ligands are in the basal positions. In a trigonal bipyramidal structure, we call this two axial positions and this three equatorial positions. So that's just the naming of the positions. And then once you form a square pyramidal structure, you have four ligands in the basal positions, right? You have four of them. And one ligand in the axial position. Now, look at the ligand in the axial position. And randomly, you can pick any two of the four basal positions. So again, three ligands. One in the axial position. Two in the basal positions. Okay? If you look at these three ligands, the bond angles are 90, 90, and 180. Again, you can bend two of these three ligands. All right, two of these three ligands, and form 120, 120, and 120 bond angles. So you can convert this square pyramidal structure back to a trigonal bipyramidal structure. However, in the new trigonal bipyramidal structure, you have two different ligands in the axial positions. Well, you may have two different ligands in the axial positions. Well, of course, just by coincidence, you can have the same two ligands occupy the two axial positions, but more likely you will have two different ligands in the axial positions. So that explains this from B to D. Over here you have this two gray spheres in the axial positions, and now you have this two in the axial positions. Pink and gray. So in this case, after this green sphere leaves, you have the two gray spheres in the cis position. So now it gets really complicated. All right, it gets really complicated. So when the 4 ligands are pretty small, the association mechanism is more likely to occur because there's space for the 5th ligand to attack the transition metal and form 5 bonds. Okay, now there are 5 bonds. Okay, it's possible. I'm just saying this is possible. All right, and if this intermediate structure is short-lived because the energy barrier of step 2 is small, the final product will be this square planar with the 2 gray spheres remaining in the transposition. However, if step 2 has a large energy barrier, this intermediate is long-lived. There's time for this trigonal bipyramidal structure to transform into a square pyramidal structure and then further transform to a different trigonal bipyramidal structure. Now with 2 different ligands in the axial position, and then, well, there's 2 gray spheres will be in the cis position. So if you see a large percentage of cis configuration in the final product, it's more likely because this second step has a large energy barrier. And also, if you see a large percentage of cis configuration in the final product, there's another possibility. You can look at the size of the ligands just to see if they are really bulky ligands. If they are really, really bulky ligands, more likely it's going to be the dissociation mechanism, and you just need to kind of just break one of the 4 bonds first, and then the metal is bonded to only 3 ligands. The bond angles will be 120, 120, 120. So imagine this green sphere left the transition metal, and then you have 120, 120, 120. And then this entering ligand, this orange sphere, may attack the transition metal from all different orientations. It can attack the transition metal between these 2 gray spheres. Then the resulting product will be trans. But this orange sphere can also attack the transition metal between 1 pink and 1 gray, and then it's going to be cis. The orange sphere can also attack from here between the pink and gray, and then that will also push this gray closer to this gray, and then it's going to be a cis configuration as well. So you see a lot of cis product, 2 possible reasons. One reason, well, over here, the second step is really slow, so it's possible for this trigonal bipyramidal structure to transform into a square pyramidal structure and then further transform into this new trigonal bipyramidal structure, and then we get cis. The second possibility is 1, 2, 3, 4. These 4 ligands are so bulky, and after this green sphere leaves the transition metal center, and then this orange sphere can attack this transition metal from 3 different orientations, either between the 2 gray spheres to form this transposition, or it can attack between the pink and the gray, or from another orientation between this pink and this gray. So let's say if this pink and this 2 gray are similar to each other, they are, for example, the 3 ligands with a similar shape, and the 3 are all good sigma donors or good pi acceptors, and then my prediction is this. Okay, if they are all bulky ligands, all right, and this one will have to leave first, and this 3 ligands, 1 pink, 2 gray, are similar to each other, you will see 2/3 of the product would be cis, 1/3 would be trans. All right, because this orange sphere may attack this transition metal between these 2 grays, or between this pink and this gray, or between this pink and this gray. This is just simple statistical factor here. So if you see a 2-to-1 ratio, well, I'm going to predict it's a dissociation mechanism. The 4 ligands are really bulky, and the entering ligand can attack the transmetal only after the leaving group has left the complex. Subsection D, temperature and pressure dependence. I'm going to show you this famous Irene equation, proposed by Irene, of course. EYRING. The reaction rate constant is kBT over H times e to the power of negative delta G double dagger over RT. Kb is the Boltzmann constant, T is temperature, H is the Planck constant. G is Gibbs energy. Delta G double dagger is just the Gibbs energy of the transition state minus the Gibbs energy of the reactant. R is the gas constant. T is the temperature. Pay attention to the negative sign. The larger the delta G double dagger, the smaller the reaction rate constant. So everything here. And we can transform this equation from here to here. We can divide both sides by temperature T. You have K over T on left. On the right-hand side, you have Kb over H times this exponential function. And we then take the logarithm of both sides. Then the logarithm of K over T is equal to the logarithm of Kb over H minus delta G double dagger over RT. But delta G is equal to delta H minus T delta S. Remember? At a given temperature. Because G is equal to H minus Ts. So delta G is delta H minus delta Ts. At a given temperature, the temperature is constant, the temperature is fixed, then delta Ts is T times delta S. That's why this delta G is actually delta H minus T times delta S at a given temperature T. Alright? And then you can expand delta G, and then you have this minus delta H double dagger over RT plus delta S over R. Alright, and this double, okay, this is not really the double dagger symbol. It's just pretty hard for me to find the double dagger symbol in Microsoft Word. So I'm using this inequality sign here. Okay, it should be double dagger. I'm sorry about that. You got this equation. So why did I move this t to the left-hand side before taking the logarithm? This is very simple. Now I can actually plot this logarithm of k over t versus 1 over t. Okay, I'm going to plot ln k over t versus 1 over t. 1 over t is going to be my horizontal axis. The logarithm of k over t is going to be my vertical axis. And you will know what the slope is. The slope is going to be negative delta H double dagger over R. That's the slope. And then if you have the experimental data of K, you have experimental data of K at different temperature, you can just pre-calculate the logarithm of K over T. You can pre-calculate 1 over T. And 1 over T is going to be your horizontal axis. The logarithm of K over T is going to be your vertical axis. Make your plot. It's going to be linear. The slope is going to be negative delta H double dagger over R. So if you have the slope, multiply your slope by negative R. That's how you determine delta H double dagger. That's the enthalpy of activation of your reaction. That's the enthalpy of activation of your reaction. And also, of course, you're going to get an intercept, the y-intercept. The y-intercept is going to be just ln kb over h plus delta s, double dagger over r. It's just this one plus this one. That's your y-intercept. Given the y-intercept, I think you can easily subtract this first. And then multiply the result by R. What do you have? You get the entropy of activation. You get the entropy of activation. You get the entropy difference between the transition state and the reactants. And then once you have delta H double dagger and delta S double dagger, you can just compute delta G double dagger at any given temperature, not just one temperature, okay? You can just calculate this delta G double dagger at any given temperature, because you have this delta H double dagger and delta S double dagger already. I want to remind you, when we do this, I implicitly assumed that this delta H double dagger is independent of temperature. This delta S double dagger is also independent of temperature. Alright, I'm assuming this is a constant with respect to temperature. This is a constant with respect to temperature. How can I make that assumption? Well, shouldn't delta H change with temperature? Yes, delta H does change with temperature. Okay, delta H is the difference between the enthalpy of the transition state and the enthalpy of the reactant. Actually, both change with the temperature, right? The enthalpy of the transition state changes with temperature. The dependence is the Cp of the transition state. The enthalpy of the reactants also depend on temperature. The dependence is Cp of the reactants, right? But it turns out the Cp of the transition state is very close to the Cp of the reactants for most chemical reactions. For most chemical reactions. As long as you're not, breaking just too many bonds and forming too many new bonds crazily, alright? So usually the transition state structure resembles the reactant structure. In that case, the Cp of the transition state is close to the Cp of the reactants. And the difference between these two Cp values is pretty small. So delta H double dagger does depend on temperature. The dependence is actually delta Cp double dagger. The dependence is Cp of the transition state minus Cp of the reactants. And that difference is pretty small. And as long as your temperature range is not too wide, okay, we're not going to do like a temperature range of several hundred degrees. Okay, if the temperature range, if you study the same reaction at different temperatures, within, let's say, 100 degrees Celsius, you can assume the integral of delta Cp double dagger times dt is pretty small. It's much smaller than delta H double dagger. So that means delta H double dagger is roughly a constant within that temperature range of less than 100 degrees Celsius. So that's why we can assume delta H double dagger is a constant. Delta S double dagger also depends on temperature. The dependence is actually delta Cp double dagger over T. So I want to tell you this delta S double dagger at temperature 2 minus delta S double dagger at temperature 1 is equal to the integral of delta Cp double dagger over T times dt from temperature 1 to temperature 2. But again, this dependence is pretty small because the Cp of the transition state cancels the Cp of the reactants approximately. So as long as the temperature range is not too wide, you may assume delta S double dagger is a constant as well. Okay, you may assume this does not depend on the temperature as long as your temperature range is not too wide. And because of these two assumptions, we can plot ln k over t versus 1 over t and determine the constant slope. The slope is negative delta H double dagger over R, assuming delta H double dagger is independent of temperature. And then we can also get the intercept, which is the logarithm of Kb over H plus delta S double dagger over R, and from that we determine the entropy of activation. Alright, so this is how we determine this, and actually it's a lot of fun to determine delta V double dagger because there's no way for us to isolate the transition state structure. It's impossible. The transition state structure is not stable. It sits on the top of an energy hill. there's no way to kind of just isolate and purify the transition state structure. If you make a lot of effort trying to do that, either you'll get the reactants or you'll get the products. All right, so you can imagine putting a really round metal ball on top of a smooth curve, on top of the heel of this really smooth curve. Right, it's not going to be stable. This ball will either roll to the left or to the right. That means this transition state structure will become either the reactants or the products. It's not going to be possible. It's not possible. It's impossible to isolate and study the transition state structure. But somehow we can determine this delta V double dagger, and that will tell us the volume of the transition state structure. Right, this delta V double dagger is the volume of the transition state structure minus the volume of the reactant structure. And it's possible to measure the volume of the reactant structure, right? Let's say you have 1 mole reactants. You measure the total volume divided by the Avogadro constant, and you get the volume of individual reactant or reactants. So how do we get this delta V? Again, we'll look at the Arrhenius equation. So I transformed the Arrhenius equation in this form. Okay, this is actually Arrhenius equation, but I can move this H to here. It's KH, and then both sides divided by KBH, and then we have KH over KBT, and then we take the logarithm of both sides. We get logarithm of KH over KBT is equal to negative delta G double dagger over RT, and then both sides multiply by negative RT. We have delta G double dagger is equal to negative RT times the logarithm of KH over KBT. Okay, it's just here. We know dG is equal to negative SDT plus VdP. You know that from thermodynamics. We use this equation for the reactants, and then we use this equation for the transition state. Now you get 2 equations, one for the reactants, one for the transition state. Take the difference between these 2 equations, and then we have this d delta G double dagger, okay, is equal to negative delta S double dagger dt plus delta V double dagger dP. Okay, so again, when you have this equation, you can apply this equation to 2 different states and take the difference, and then you get d delta G is equal to negative delta S dt plus delta V dP. All right, and then you hold the temperature constant. Okay, you do this measurement at a given temperature. dt is 0, and then you have d delta G is equal to delta V dP. All right, and then delta V is simply d delta G over dP. So that's why delta V is d delta G over dP. Okay, delta V is d delta G over dP. Okay, this equation applies to just any change in state of a system. And also you can, apply this equation to the change of the state of the system from the reactants to the transition state. And then you can put double dagger here. All right, double dagger here. Again, I'm just too lazy to find the real double dagger symbol from the table of symbols in Microsoft Word. And then I plug in delta G double dagger. It's right here. Okay, and then we're doing this measurement at a given temperature. No temperature change. Okay, no temperature change. Make sure you hold temperature constant. That's why you can take this negative RT out of this differential. You have negative RT here. And over here inside, it's just the logarithm of KH minus the logarithm of KH over KBT minus LNT. Minus LNT, right? Minus LNT. And then you have a negative sign here, okay? And minus LNT, so you have another negative sign over there. So I made a mistake early on. You have a negative sign here, and over here, negative LNT. This is negative LNT, all right? Because logarithm of 1 over t is negative LNT. And we got this equation. So now it's pretty simple. You do this measurement of the reaction rate constants at a constant temperature. Okay, do not change the temperature this time. Just change the pressure. Measure the reaction rate constant at 1 bar pressure, 2 bar pressure, 10 bar pressure, whatever. And then you plot this LNK. You plot LNK versus P. Okay, you plot LNK versus P. Okay, it's going to be linear. Okay, it's going to be linear. And you find the slope. The slope is going to be delta V double dagger over RT. The slope is going to be delta V double dagger over RT. So you find the slope of LNK versus P. Multiply your slope by RT. You get delta V double dagger. I mean, how exciting it is. You can actually determine the volume change between the reactants and the transition state. Okay? It's just, you just need to measure the reaction rate constant at different pressures. That's it. Now, qualitatively, of the rate limiting step is associative. Okay? We're focused on the rate limiting step, right? If you have a sequential mechanism, one step is much slower than the other. The slow step, the really slow step, is the rate limiting step. Okay? If that's associative, then both delta S double dagger and delta V double dagger will be negative because the transition state structure is more compact than the two reactants, right? This is a association reaction between two reactants, right? The transition metal complex is one reactant. The entering ligand is another reactant. So this is going to be a combination of these two. And that will cause the entropy decrease and volume decrease in the transition state structure. So now let's get backward. If you measure the reaction rate constant at different temperatures to get the temperature dependence. And then you measure the reaction rate constant at different pressures to get the pressure dependence. And then you can determine delta S double dagger. You can determine delta V double dagger. If both are negative, you can be sure that the rate limiting step is associative. This mechanism is called associatively activated. Okay, it's associatively activated. But the mechanism can still be dissociation or interchange or association. It's just the rate limiting step is associative. Okay, so no matter your mechanism is an associative mechanism, dissociative mechanism, or interchange mechanism, there are two steps. Okay, there are two steps. Sequentially, there are two steps. The slowest step is a associative reaction. If both delta S double dagger and delta V double dagger are negative, when you plot this LNK versus pressure, or when you plot this LNK over T versus 1 over T, and you get intercept to determine this delta S double dagger. I mean, of course, this is this data analysis is a little bit more complex. I mean, you have to plot LNK over T versus 1 over T, and then you get the intercept. And the intercept subtract this term, and then multiply by R, you get delta S double dagger. But it's doable. It's doable. It's possible to determine delta S double dagger. Over here, this is more straightforward. You plot LNK over P, and you get the slope multiplied by RT, you get double V double dagger. But anyway, you can get this too. If they are negative, the rate limiting step is associative. This mechanism is associatively activated. Okay, now let's look at some experimental data. We have some ligand substitution reactions of those transition metal complexes. delta S is negative, delta V is negative, delta S is negative, delta V is negative. So all those reactions are associatively deactivated. Finally, the first order pathway. So sometimes when we do ligand substitution in a solvent, and this solvent consists of the entering ligand, it's actually a second order reaction, but the concentration of the entering ligand remains constant. So we want to call this pseudo first order.